Okay, let's hope this works. I'm recording from a distance. I hope you can hear me. So this was the lesson today, 2.3-1, finding the zeros of polynomials. We're splitting this lesson over 2 days. By the end of the 2 days, you should be able to answer these two questions. What can we do to find the zeros if the polynomial is very difficult to factor? How can we tell if an x value is a zero of a polynomial? So this was the warm-up. Pause your video, give it a go. And going over this quickly. So write out a polynomial that has the following zeros. First of all, the polynomial needs to have a name. Let's call it f of x. And you're going to turn these zeros into factors. You should bear in mind that whenever you have an irrational zero, they always come in conjugate pairs. There won't be just plus root 5, there'll also be plus and minus root 5. So if you have a zero, it's come from a factor. For instance, if you had the factor x minus 5, if that was the factor, the associated zero would be x equals 5. If you're given a zero, x equals a number, that implies that there's the factor x minus c is a factor of your polynomial. So let's take all of these. If I have 0, that's come from x minus 0 as a factor, which obviously is just x. Minus 2 has come from x minus minus 2, which is like x plus 2. And then I've got these 2. So I've got x minus the positive square root of 5 and x minus the negative. So if I'm subtracting the negative, I'm adding the square root of 5. Okay, now we don't like that answer because we don't like having this bit here. If you look at what you've got here, you've got a pattern. You've got a minus b times a plus b, which I hope you're starting to recognize is otherwise known as, oops, let's get this out of the way. Shove it somewhere, we'll put it down there, okay? It's difference of squares. Whenever you see, you're going to see this pattern so often in math this year. Whenever you see a minus b times a plus b, that is the difference of squares, and it can be rewritten as a squared minus b squared. So I'm going to square the x. You're really getting it from x times x. It's going to be x squared. Your outer and inner terms cancel each other out in this, you see. You've got x times root 5 plus root 5x minus root 5x. Put those together, they cancel each other out. So you really just get your first and your last term squared. So let's write the whole thing out from the beginning. We have x times x plus 2, and then this bit that we've got written in green would turn into x squared minus difference. It's the difference of squares. This would never be plus, just wouldn't work with plus. And then you have, the last term would be the square root of 5 squared, and remember if you're squaring a square root, those cancel out, you just end up with 5 there. So here is a possible answer to this question. Okay, now for this one, factor, then sketch the graph. On this one, we are going to factor by grouping. So how to group them? We'll group that one here, and group this one here. You can pull out a GCF of 4x squared, which leaves you with x plus 5 from that first group. Now I need to decide if I'm going to write plus or minus. Looking at those two, I'm definitely going to subtract a negative. I'm going to factor out a negative. I'm going to factor out negative 5, which leaves me with x plus 5. So I'm really happy at the moment because these two match, which means that they are a factor. It's a factor of this and a factor of that, so it is a greatest common factor. It's a GCF. I can factor it out and write what's left. And now I'm factoring. These are multiplication happening there. 4x squared minus 5 is what was left. But I've got to graph that. And this is still not fully factored. Look what I've got here. I've got a squared minus, it doesn't really look like something squared, but it is. I've got difference of squares again. This time I've got, oh, it's locked. I've got this side. And this can be factored to be a minus b, a plus b. So my a squared is 4x squared. Wherever I see an a, I'm going to write the square root of 4x squared, which is 2x. And wherever I see, for the b squared is 5, wherever I see b is here, I'm going to write the square root of 5. So let's write this fully factored. We have x plus 5, then this would be 2x plus the square root of 5 times 2x minus the square root of 5. So to graph it, I'm going to need the zeros. This is x equals negative 5. This one gives me x equals negative the square root of 5 divided by 2. And this one gives me positive the square root of 5 divided by 2. So put these on a graph. Oh, first of all, end behavior. You've got a choice. They're going to be the same. When you've been given it in general form like this, it's just your lead. They're all terms. You've got 1, 2, 3, 4 different terms there, and we just need the leading term. So the leading term is 4x cubed, which is positive, and that's an odd number. So positive, end up here, odd number down here. So that's our end behavior. If we hadn't been given it in standard form as a list of all these general form, all these terms added together, I could have got this from factored form. To get your leading term from factored form, you have to take the leading term within each factor and multiply it together. So you'd be multiplying x times 4x squared, and you would still end up with 4x cubed. It'll give you the same answer, and it should, because they're all equal. Everything you're doing here is equal. So now I need a graphics. Let's put this on a graph. First zero, 1, 2, 3, 4, 5. And what behavior would it have? Let's look at the multiplicity. Oh, they're all boring. 1, 1, 1. They're all just going to cut. Okay, now I've got to... I got to put those on my graph. Let's think about how big are they? The square root of 5 over 2. I could compare that to the square root of 4 over 2. That's the nearest perfect square I can think of. And so this one, what we're looking for must be a bit bigger than it. So it must be a bit bigger than 2 over 2. So that's a bit bigger than 1. So it's probably, I don't know, about 1.2, 1.3. That will do in terms of graphing it on this scratchy little graph over here. So we've got one of them a bit more negative than negative 1, and one of them at about 1.3. So one's at about negative 1.3, and the other one's at about positive 1.3. Now graph them. Oh, and they were both just cutting across. So for the graph, I'm looking here at where my end behavior, I know I'm going to start sort of low and hope I end up high. So cuts, cuts, yay, it worked, ended up high. And I could work out that y-intercept if I wanted to by plugging in 0 into my equation, and I would end up, when I did that, with negative 25. And that makes sense because it's underneath the x-axis, so the whole graph fits together. Homework, we're splitting the homework in two. You're going to do these problems today, those problems after the weekend. They're actually going to go in the next grading period. You need to have done these ones today because you have a quiz tomorrow, and it's all going to be due tomorrow morning. Well, tonight would be good. Right. So that was the warm-up done in another class. Here we go. Notes. Write down these notes on the remainder theorem. The remainder theorem says if you evaluate a function, we're evaluating for x equals c, whatever this number, this would just be a number there that would come out once you've evaluated it, and that coincidentally turns out to be the remainder if you actually did this division. If you got your polynomial and divided it by what you're looking and hoping is a factor, where this c here was the c, the value you put in here, okay? And you know that x minus c turns out to be a factor if when you divide it, the remainder is 0. So how we can use the remainder theorem is we can just put values into a function, and if the function evaluates to 0, we know we found a factor. I'm going to be doing that more next week. Now, the first thing we've got to look at, though, is we're obviously going to be dividing polynomials, and that's what today's lesson is all about. So the first thing we're going to do is just remind you how you first learned to divide nasty, horrible things. If I had the number 208 and I wanted to know if 12 was a factor of it, well, now what I'd do is I'd pick up a calculator and do 208 divided by 12 and say, no, it's not a factor, because it doesn't come out as a nice, pretty number. But when you were in, I don't know, elementary school, you learned to do long division. You put the top dog in the house. Now write this out. This is important because it's going to help you understand how we do long division with polynomials. Top dog in the house, the 12 outside. How you divide, you say how many times does 12 go into 20? Well, it goes in one time. And then you multiply back. 1 times 12 is 12. And then you get these two lines and you subtract and you end up with 8. Then you pull down your next number and you say, does 12 go into 88? Well, obviously, 88 is a lot bigger. And it actually happens to go in 7 times. And then you have to multiply this back. So you do 12 multiplied by 7. 2 times 7 is 14, carrying that 1. 1 times 7 is 7, plus that 1 is 8. So it's 84. You multiply it back, put that here. And then you have to subtract these two lines, which leaves you with 4. There's nothing more to drag down, so we finished. So this was the remainder. The remainder was not 0, so 12 is not a factor. But we want to actually write the remainder into our answer. This is our quotient so far. Our quotient would be that 17 plus this remainder. This remainder hasn't been divided yet by 12. So our answer would be, we add that on. We add on 4 divided by 12. Our quotient on this problem is 17 and 4/12, which simplifies to 1/3. So that would be our answer. And we've just found out that 12 is not a factor. So let's now go and do this with polynomials. So there's 2 ways of dividing polynomials, with long division and with synthetic division. And when I see this, I'm definitely going to use synthetic division, but I'm going to use this example to teach you. It just makes it easier to teach from using them like that. Synthetic division is so much quicker and less to write and easier than long division that we like to use synthetic division as often as we can. However, if you're ever trying to divide by something where you've got an x squared, you can't use synthetic division. This one here, when we come on to this problem, this is something we call an irreducible quadratic. That means quadratic. It is a quadratic equation that doesn't have real roots. This, if that was a factor of the polynomial, it would turn out to have actually complex roots. Okay? Those wouldn't be x-intercepts on the x-axis. So let's go through long division. We're going to use the same process we just used to divide 208 by 12, but we've got this. We've got 6x cubed minus 2x squared plus 5x plus 1, and we're going to divide it by x minus 1. It's the same idea. Put the top dog in the house and the divisor on the outside, but now we have to step through. The first thing we do is we get 6x cubed and we divide it by x. That would give me 6x squared. Then you multiply that back, not just over the x, but over the minus 1 as well. You don't normally write those arrows, but I'm trying to show you what I'm doing here. So 6x squared multiplied x gives you 6x cubed, and 6x squared times minus 1 gives you minus 6x squared. Now notice these line up beautifully, and now you have to subtract. When you're subtracting, these can get really long. You can miss the fact halfway along the line you're supposed to be subtracting. So I think it's easier to add the opposite. So just go through this line that's in green and flip everything. Multiply it by a negative. We're subtracting that, we're subtracting that. It will flip them. So now I've got 6x cubed minus 6x cubed, which is nothing, but we don't tend to draw the nothing because that would, it just makes your work look messy. Now we've got minus 2x squared plus 6x squared, which gives me 4x squared. And now it's time to bring down our next term. And we repeat the process. So here we go. 4x squared needs to be divided by x, which gives me 4 plus 4x. Put that up at the top. Multiply it back over these two. Don't do these arrows all over your work. It makes it look really messy. 4x squared, 4x times minus 1 gives me minus 4x. And then remember that we are actually subtracting this blue line. So flip everything. Now this would give me 0, but remember we don't bother writing that. It messes up your work. 5x plus 4x gives you 9x. And now bring down your last bit, plus 1. And go through it all again. So 9x divided by x gives me plus 9. Multiply that back. Plus 9 times x gives me 9x. Plus 9 times minus 1 gives me minus 9. And I have to subtract that line. So I'm running out of which colour shall I use? There, we'll use pink. So if I'm subtracting it, I have to flip everything. Nothing plus 1 plus 9 gives me 10. This is my remainder. My remainder still hasn't been divided by x minus 1. So my answer to this problem would be 6x squared plus 4x plus 9. Now you have to add on a fraction. You put the remainder at the top. You put what you wanted to divide it by underneath. Okay, next example. This one here, it's the same that was on the last screen. I'm just giving myself more room. This one you have to do by long division. You couldn't use synthetic division. And what you've got to look out for here, do you see in this first problem we had x cubed, x squared, x the 1, and this would have been like x the 0. Nothing was missing. But in the example we did in the warm-up, we had 208, which is 2 hundredths, which are 10 to the power 2s. We had no 10 to the power 1s, and we had 8 ones, which are 10 to the power 0s. If I didn't bother writing, if I had no 10 to the 1s, and I just wrote this as 2 and 8, people might think I was trying to write 28. If you've got a power of your base missing, you've got to put it in, otherwise you'll go wrong. So look at what we've done to you on example number 3 here. We've got no x to the power 1s in dividend, and we've also got no x to the power 1s in the divisor, what we're trying to divide by. So we have to put those in place when we write it in here. Oh yes, I did have one I prepared earlier. So pause your video, give this a go, and then I'll come and I'll go over it with you. So here we go. 6x cubed divided by 2x squared gives you 3x. Put that up here. Multiply it back. 3x times 2x squared is 6x cubed. Just done that bit. 3x times nothing is nothing. So we've got no x squared. That was this bit. Then I've got to multiply it by 1 and put that here. Plus 3x. Then I have to think, okay, I've got to subtract these. So when I'm subtracting, I add the opposite. Opposite, opposite, opposite. This gives me nothing. Don't bother writing the nothing. Only if it's at the beginning, yeah? Only if it's the first thing. 10x squared minus nothing gives me 10x squared. Nothing minus 3x is minus 3x. Bring down your next number. And do it again. 10x squared divided by 2x squared gives me 5. Add on 5. Multiply that back. I get 10x squared. 5 times nothing, no x's is no x's. And then 5 times 1 is 5. Remember that you've got to subtract this line. And how we're going to subtract the line is we're going to add instead of subtracting by making all of these their opposites. So we've got nothing minus 3x minus nothing is minus 3x, plus 8 minus 5 is plus 3. I cannot divide this any further. I cannot divide 3x by 2x squared, so this is my remainder. What to do with your remainder? Add it on as a fraction. The remainder goes in the numerator, and what you were trying to divide it by goes in the bottom, and you don't need to put in that 0 term this time. So that was long division. Let's finish this video and start a new one. Oh, okay, the video is going to finish in a minute.